Okay, today we're going to look at quantum calculations. Essentially what we're going to do is look at equations using Planck's equation for energy. Alright, remember E is energy, and we're going to use the unit of joule for that. I'll talk about that in just a little bit. H is a constant, and it's known as Planck's constant, and it's going to be 6.63 times 10 to the minus 34 joule seconds. Now we don't always draw the dot in here. I'm drawing the dot in here to separate out these units. We have the joule for energy and the seconds because we're going to need that when we talk about frequency, because remember frequency's units, the unit for frequency is that inverse second. So when we multiply these two together, those seconds and inverse seconds will cancel out. You'll see that just in this first calculation. So remember this V is not really a V, but the Greek letter nu. And it represents the frequency of the electromagnetic energy. In this case, we're going to look at blue light emitting some frequencies. Okay, so what we're looking for in number one, or this first question here, is we're looking for energy. Now the unit that we use here is a joule, which is a capital J. We'll talk more about joules a little bit later, but it's Joule, named after James Joule, the man who came up with this idea of energy not being a substance. Anyway, we'll get to that a little bit later. All right, what we're given is frequency. All right, we know that the frequency is 6.00 times 10 to the 14 inverse seconds. All right, we're just simply going to plug right into this equation. So E equals H times nu, when H is 6.63 times 10 to the minus 34. And these energies are all going to be very small because of this unit of Planck's constant. Because Planck's constant is such a small number, it's going to make a lot of these energies come out really, really small when we do these calculations. To the 14 inverse seconds. Notice that this is seconds, and inverse seconds cancel out, leaving us with the unit of joule, and that's why we need that unit in here. This is known as a proportionality constant in science, and the connection between frequency and energy is that the higher frequency is, the higher the energy. This is known as a direct proportionality. As this goes up, the energy goes up. Frequency goes up, energy goes up. Direct proportionality, as opposed to the speed of light equation, where if we saw that the wavelength went down, then my frequency went up. This is an inverse proportionality. It's very important to kind of understand the connection between those two. All right, you get your calculators out, plug into the number, plug this in your calculator, and you should get 3.98 times 10 to the minus 19 joules. Now, a little tip here, if you are ever doing these calculations for any color of light, it is always going to be to the negative 19 joules of energy for all of the light, whether it's red, yellow, green, blue, indigo, violet. Doesn't matter. It's always going to be to the negative 19 joules. All right, and it's the simplest calculation we're going to see. Now, let's take a look at another one. It's a little more complicated, not much, but so here we're going to determine wavelength. So now we're looking for wavelength. All right, so wavelength of a microwave radiating with this amount of energy. So we know that the energy coming out of this microwave is 1.99 times 10 to the minus 23 joules. All right, so again, we're going to use the equation, Planck's equation for energy. I'm going to use that speed of light equation, because what we're looking for is wavelength. Well, if we're looking for wavelength, we're going to use this equation to solve for wavelength. Well, wavelength is equal to the speed of light over the frequency. So I need to know frequency. Well, if I know the energy and I know frequency is here, I can solve for this equation, solve for frequency, right? And I can divide that by h, by Planck's constant, and I can take this frequency, plug it into here, and then I can solve for wavelength. That's the general idea. So I'm taking two equations and I'm kind of manipulating them and joining them together by solving for the common variable between the two. All right, so first thing to do is to solve for frequency using the equation I just derived over there to the right. E is the energy, 1.99 times 10 to the minus 23rd joules, over Planck's constant, which is 6.63 times 10 to the minus 34 joule seconds. Now joules cancel, leaving me with 1 over a second, which is what I want for my frequency calculation. So my frequency comes out to 3, not 1, but 3.00 times 10 to the 10 power. That would be inverse seconds. Then I'm going to do is take that and plug it into this equation and solve for the wavelength. So my wavelength is the speed of light over my frequency. So 3.00 times 10 to the 8th meters per second. All of that over my frequency, which I just calculated, 3.00 times 10 to the 8, no, to the 10. This time it's 10 to the 10 power. And that would be inverse seconds. These cancel out, leaving me with meters, which is exactly what I want for my wavelength. It should be in a meter. And if I cancel these two and divide, I end up with 1.0 times 10 to the minus 2 meters. And there is my wavelength. Okay? All right, a couple things to think of when you're doing these. Don't forget the units. The meter is for wavelength, inverse seconds for frequency. Watch unit conversions because you're going to see sometimes the units aren't the same. So watch to make sure units are connected together and unified. All right, here we're going to calculate energy again. Okay, this is a Bohr's problem. Okay, Bohr's model problem. Why is this a Bohr's model? Because we've got electrons dropping and increasing from n equals 2, n equals 4. So we've got the nucleus in the center with the positive charge, n equals 1, n equals 2, n equals 3. I'm going to run out of room for 4, but you get the idea. We got n equals 4. So we're looking for an electron. It's a terrible drawing, but I think you get the idea here. The electron is sitting in n equals 4, and it's going to drop down to n equals 2. Remember, each one of these is n equals 1, n equals 2, n equals 3, n equals 4. When the electron drops down to this energy, it is going to release energy. Energy is going to be emitted from this atom. In this case, the energy that's emitted is what we're trying to calculate. Well, we can't measure the energy directly. What we do is we measure the wavelength. So if we know what the wavelength is, we can then figure out what that energy is by using the wavelength. Well, my wavelength is equal to 486 nanometers. Hopefully you know right away to get rid of nanometers, right? Get rid of nanometers, convert that to meters. 1 times 10 to the negative 9 over 1. I will give you this conversion. I didn't in this problem, but I would on tests and quizzes. So your wavelength, when you calculate that, should be 4.86 times 10 to the minus 7 meters. Okay? So I've got my wavelength in meters. I'm going to undo what I just did in that last problem. In the last problem, I had the energy, and I found the wavelength. Well, I'm taking the wavelength and finding the energy. So I'm going to go backwards. I'm going to find my frequency, and I'm going to solve for frequency by plugging into the speed of light equation. C equals wavelength times frequency, and I can derive that equation. 3.00 times 10 to the 8th meters per second over my wavelength, which is 4.86 times 10 to the minus 7 meters. Cancels out, leave me with that inverse seconds again. Again, I'm always checking my units, making sure everything is working out. I'm looking for energy. The unit should be a joule when I'm finished. So my frequency, when I get to this part, should be 6.17 times 10 to the 14 inverse seconds. Okay? Then I take that and plug it into the Planck equation. And that would be 6.63 times 10 to the minus 34 joule seconds. And just like it did in that first problem, I'm going to multiply these two numbers together to the 14 power. Inverse seconds are going to cancel, leave me with a unit of joule, which is exactly what I want. And I can calculate the energy. So to be honest, these problems with Bohr is really not much different than when calculations for the first two. It really is, other than the fact that we're applying this energy to the electrons in an atom. So this would be to the negative 19 joules. Okay, and that would be the energy, and there's your calculation. So this is the amount of energy that's coming out of one electron as it emits energy from Bohr's model. All right, anyway, that's pretty much it. So I will see you guys in class. We'll look at these a little bit more, and I'll take some questions. See you later.